Hello, welcome to another online lecture for Gödel's incompleteness theorem. We had a snow day today, so I wanted to perhaps go over some of, at least part of the lecture of what I was planning on doing today. So today's lecture, I want to continue our discussion of Robinson's Q. So as a reminder, we have a first-order language. We have equality in the language, and then we have our constant symbol 0 and three function symbols, the successor function, plus, and times. And then on top of that, we build our first order language. So the atomic formulas are just formulas involving equality, so equations, and then you have quantifiers and so on in the language. We talked about this in class. Now, just as to be very clear about the intended structure, our intended structure is the natural numbers with 0, successor, plus, and times. So this is a first order structure. 0 is a constant symbol, s is a function symbol, as are plus and times are also function symbols. So the domain is going to be the set of natural numbers. This is our intended structure. The interpretation of 0 is, of course, the number 0. The interpretation of s is the successor function, so you just add 1 to a natural number. The interpretation of plus is plus. This should really here be boldface, but it's not showing up properly. So I take it that this sort of ambiguity here won't confuse anybody. And the interpretation of times is, of course, times. It's the multiplication function. Okay, so that's the intended model. Of course, I've just defined a first-order language, and I can interpret that first-order language in any structure at all. But this is our intended model. So this is the intended model. Now, again, as a reminder, for each natural number, there's a term in the language that refers to that natural number, or that names that natural number. And we call this the numeral n. So I'll draw it with a boldface n with a line over top. And that's just going to be n s's followed by a 0. So this is a term in our language, n s's. So I take n of the symbols s, n of those, followed by a 0, and that of course, the interpretation of that is of course the natural number n. So for each natural number, there's a corresponding numeral, a term in our language that picks out that natural number. Now, the axiom system is going to be a little bit easier to state than baby arithmetic, which we talked about in class. Because baby arithmetic doesn't have quantifiers in it. So these axioms will look a little bit more normal, so to speak. So the axiom system is called the axiom system Q. Of course, we assume some axiomatization of first-order logic. So that's sort of in the background. I'm not going to state explicitly what that is. I presume we all know what that axiom system is, or whatever. You just choose your favorite axiom system. But there are 7 additional axioms. The first 3 axioms, you can think of these axioms as describing or explaining how the successor function works. Axiom 4 and 5 are axioms regarding addition, and axiom 6 and 7 are axioms regarding times. So the successor axioms, we sort of came across these in a number of different situations. First of all, for any x, the successor of something can never be 0. So 0 doesn't equal the successor of anything. For any x and y, successor is a one-to-one function. So if sx equals sy, that means x has to be the same as y. This is axiom 2. And then axiom 3 says that every non-zero element in the domain must have a predecessor. So if x is non-zero, then there must exist a y such that x is the successor of y. Addition anything plus 0 is, sorry, that's a mistake. This should be x. X plus 0 is x. Axiom 5, this tells you how successor and plus interact. So if you just take x plus y plus 1, that of course is just going to be x plus y plus 1. Axiom 6, anything times 0 must be equal to 0. And this axiom 7 then tells you how times and successor interact. So again, think of it as if you take x times y plus 1, the usual distribution property tells you that should be x times y plus x. Okay, so these axioms make good sense. It's easy to see that they are all true on our intended models, on the natural numbers. And so the question is, well, so what can we prove with this axiom system? Now, sort of as a sanity check, we can first see that Q can prove that 0 plus 2 equals 2. So that, well, the constant 0 plus the numeral 2 must equal the numeral 2. So really, you know, again, so this is showing that two terms, we can prove that this atomic formula is true, or you can derive this atomic formula. So this is 0 plus the successor of 0 equals the successor of 0. And that's what we want to prove. All right, so let's see how we do that. In order to do that, we really just need the axioms involving plus. And so here are, just as a reminder, I fixed axiom 4 here. Here are the two axioms involving plus that we will need to use. All right, so we want to prove, so this is the claim, so we want to prove that 0 plus successor of 0 is equal to successor of 0. Okay? Now, the general fact about first-order logic, or the general first-order axiom that we're going to use is for all x of x implies for all x where you take x and you can replace it with any term tau. So we're going to use this all the time. We're going to take if we know for all x 5x is true, then we can replace x with any term that's substitutable for x. So there's a side condition. Not all terms can always be substituted for x. This is just a reminder. In this case, the formula we're concerned with doesn't have any quantifiers in that, so we don't have to worry about that extra, the typical side condition that you need to worry about. Okay, so just look at axiom 5 and take an instance of axiom 5 where, so for axiom 5 here, I'll use this kind of as a scratch pad. So let x be 0 and y be s of 0. So if you do that and plug those values in for x and y, we get 0 plus successor of 0 is equal to successor of, and then x is 0 plus successor of 0. So this is an instance, well, I'll just write axiom 5. This is an instance of axiom 5. Okay. All right. So we're able to see that. Now we we need to replace 0 plus successor of 0 with something. So we have another instance of axiom 5. Here again we're going to let x equal 0, but this time we want y to be equal to 0. Okay. So if x is 0, it's going to be 0 plus, and now y is 0. Successor of 0 is equal to successor of, now x is 0, and y is 0. So again, this is an instance of axiom 5. Okay? Now we note that 0 plus 0 must be equal to 0. So this is going to be an instance of axiom 4 where x is just set to 0. Okay, so if we let x be 0, then anything plus 0 must be that same thing, but in this case x is 0. Okay. Now what we do is we apply Leibniz's law twice. So this is replacement of equality. So we know that if we can prove tau equals sigma and phi of tau, then we can always derive phi of sigma. Okay, so we've been able to derive that 0 plus 0 is equal to 0. So I can take, in this formula right here, I can replace 0 plus 0 with whatever it's equal to. So I know that 0 plus successor of 0 must be equal to successor of, now I replace 0 plus 0 with 0. So it's successor of 0. So I'll write LL for Leibniz's law. Okay, and now I want to do that again. So 0 plus successor of 0 equals successor of 0. So I go back up to this formula right here, and I see that 0 plus successor of 0, I can replace that with whatever it's equal to. So I get 0 plus successor of 0 is equal to successor of, and now instead of writing 0 plus successor of 0, I'll write whatever it's equal to, so that's successor of 0. So again, that's Leibniz's law. So in that way, I've been able to derive, using just these two axioms and some facts about first-order logic together with Leibniz's law, that 0 plus the numeral 2 must be equal to the numeral 2. Okay, now it should be easy to see that we can generalize this and in fact prove that 0 plus any numeral n is equal to that same numeral n. You just apply the exact same proof. It'll just take, well, if you think of that proof as being one chunk of the proof, you'll have to do that, I think, n times or maybe n minus 1 times. I don't know. Figure out how many times you need to do it. But you just repeat that style of proof over and over and over again until you're able to prove that you'll be able to derive for any natural number that 0 plus the numeral n is equal to the numeral n. Okay? However, we know that Q is a sound theory, but we can actually prove, it's very easy to see, that Q cannot be negation complete. Q, there are formulas in this language such that Q can neither prove it nor its negation. And it's interesting to see. So here's an example of a formula that cannot be proved in Q. We can't prove for all x 0 plus x equals x. Okay, so just think about that for a moment. We have, so over here we have as an axiom, we've assumed that, so one of our axioms is for all x plus 0 equals x. So that's an axiom, so surely we can prove that because that just takes one step. We can prove for each natural number, we can prove 0 plus the numeral n must be equal to the numeral n. So every instance of this axiom can be proved. Well, every instance involving the natural numbers. But we can't prove the generalization of this fact. We can't prove the general arithmetic law that says for every natural number, 0 plus that natural number must be equal to the natural number. Okay? So that's what I want to, for the rest of this lecture, I just want to explain to you why, how we know that Q can't actually prove this formula right here. All right, now one way to show that a set of axioms can't prove a particular formula is to construct a model. So we want to construct a model. So our goal is construct a model of Q where for all x 0 plus x equals x is false. So that's what we're trying to do. I want to build the model Of course, it has to be a non-standard model. It can't be a model. It can't be the intended model, because this is a true fact about the natural numbers, that for any natural number, 0 plus that natural number is equal to the natural number. So I want to construct some, you might call it a deviant model, where this formula is actually false. Okay, but it can't just be any model. Of course, it has to be a model where all the axioms of Q are true. So I've been able to find a model where all the axioms are true, but this formula is false. So if this is, so it can't possibly be the case that this formula, that Q can prove that this formula is true. All right, so what is our model? So our model is going to consist of the natural numbers together with two extra elements, A and B. We're going to have in our model a way of interpreting the successor function. We're going to have a way of interpreting the plus function, and we need a way of interpreting the times function. And of course, we need a way of interpreting the constant 0. So the interpretation of 0 is just going to be the natural number 0. The successor function will work as follows. So the successor function of n, where n is a natural number, is just going to be the old successor function. So there's the usual successor function. So this is for n, which is a natural number. Now, what I'm really interested in, what does the successor do on these deviant, these new elements of the domain? So successor of A is just going to be A, and successor of B is just going to be B. And now what about plus? How does plus work? Well, what plus is going to do, so if n and m are natural numbers, then of course I'm going to want my interpretation of plus to just be the usual addition for natural numbers. I'm going to want to say that A plus any natural number, so plus star of any natural number, is going to be A. B plus star of any natural number is just going to be B. But now, if x is any element of n or A and B, so it's any element of the domain, if A is on the left of the this new plus star sign, so x plus A is going to be B, and x plus star of B is going to be A. So if you have a natural number to the right of this new plus symbol, then A plus that will just be A, B plus that will be B. But if you have one of the deviant elements of the domain, so either A or B to the right of this plus star, then all you're going to do is you're gonna flip. So anything plus A will be B, and anything plus B will be A. We also need an interpretation of times, but I'm going to leave that as an exercise for you guys to complete. So I'm going to one of your homework exercises is going to be to fill out this model, so we have a full interpretation of our language, because all we really care about for the purposes of this fact is just plus. Okay, now what do we need to know? We need to know, does this model satisfy, make all the axioms of Q true, and does it make this formula false? So over here we see, just as a reminder, this is the interpretation that I gave for. So we have a new successor symbol. So the interpretation of our successor function symbol is going to be S star. Interpretation of plus is going to be plus star. And interpretation, and this is how plus star works and S star works. And now we can see that this formula is false. So this is just false by definition. So 0 is interpreted as 0. Just let x be, for example, a. And we have 0 plus the new this must be equal to b. Because this is how this new plus function, this is how that works when a is on the right-hand side. I could have also taken x equals to b. It doesn't matter. But anyway, I have it set up so that this formula is actually false. So we see that this formula is false, but that's not enough. We want to be sure that our interpretation is actually a model of Q. So I'm not going to prove all of that in detail because that would get a little bit tedious. But let's just go ahead and see, I'll kind of run through and explain each of the relevant axioms. So we never let S star be equal to 0 because neither A or B are equal to 0. In fact, they can't be equal to any of the natural numbers, so they're completely new symbols in the domain. And of course, our old successor function never sends a natural number to 0. So axiom 1 is indeed satisfied. What about axiom 2? Well, this successor function, the old successor function is of course 1-to-1. So if x and y are natural numbers, then indeed the successor function is going to be 1-to-1. So this will be satisfied. And of course, the extension to how the successor function works on the new symbols is also 1-to-1 because A gets uniquely mapped to A and B gets uniquely mapped to B by the new interpretation, by this S star function. Okay, so axiom 2 is satisfied. Axiom 3, also easy to see it's satisfied because for all natural numbers, the interpretation of S star is just the old successor function, which indeed satisfies this axiom right here. And the new interpretation does because we can just let, so if x is equal to a, we let y equals a, and if x is equal to b, we let y equal to b. And we have, a equals successor of a and b equals successor of b. Okay, so it's easy to see that these first three axioms are satisfied by this interpretation of S. Now what about axiom 4? Well, axiom 4 is going to be satisfied because if we let x be any element of the domain, so any either natural number or a or b, we see that that natural number, well, let me just write it as x plus 0, so this is plus star of 0, must always be equal to x, because if x is a natural number, then any natural number plus 0 will of course be x, because plus star is the old addition, the usual addition. But if x is equal to a, then indeed a plus any natural number is going to be a. So in particular, a plus 0 will be a. Same thing for b. Now what about axiom 5? Again, if x and y are interpreted as natural numbers, then axiom 5 is satisfied because plus the interpretation of plus reduces to the usual plus. But now what happens, for example, if, let's say, x is equal to 0 and y is equal to a? So we can just run a simple calculation. So we have x plus, this should be 0 plus successor star of a should be equal to, well, so what is this going to be equal to? So that's going to be 0 plus, this is plus star. 0 plus star of successor star of a is just a. And now we have, if a is on the right, anything plus star a must be equal to b. Okay, so now let's see, s star of, now x is equal to 0 and y is equal to a. Okay, so again, anything, if a is on the right, 0, anything plus a on the right gets interpreted as b, so this is going to be successor star of b. But by our definition, is of course just b. So when x is equal to 0, and it's easy to see it doesn't matter as this works as long as x is any natural number. It doesn't really matter as long as x is any natural number and y is equal to either a. The same argument, similar argument holds if y is equal to b. So let's kind of reverse it. What happens if x now is equal to a, but y is equal to, say, some some natural number, say, let's just say 0. So again, we're going to have a plus star successor star of 0. That's going to be a plus star of 1, which is going to be equal to, because if you have a on the left-hand side, this is just going to be equal to a. Okay, and now, so let's just see what happens if we do successor star of, now x is a and y is 0. So this is going to be successor star of, now a plus star of 0 is of course just a. And if you apply successor star of that, that's again equal to a. So verifying axiom 5 is just going to be going through lots and lots of examples. I suppose one more example that we can do, so we'll do this example up here, is what happens if x is equal to a, but y is equal to b. So this will also test your understanding. In fact, you should probably pause and figure out what the answer should be. Work out why axiom 5 is true, but I'll go ahead and do it now. So a plus star successor star of b, well, that's going to be a plus star of b, which is going to be, if b is on the right-hand side, that's always just equal to a no matter what is on the left-hand side. Okay, so now let's look. Successor star of a plus star of b. We see, of course, again, if b is on the right-hand side, then anything plus star of b must be equal to a. So, and successor star of a is just equal to a. Okay, so hopefully that should have convinced you that axiom 5 actually is true. I think I've actually run through all of the cases. So we see that this model here is a model of all of the axioms. Actually, I only have a partial model because I haven't interpreted times yet. But it's a model where this formula is actually false. So I have a model of all the axioms where this formula is false, so it can't possibly be the case that this formula, that Q can actually prove this formula. Because if this formula is derivable from Q, then any model of Q must make this formula true. Okay, now one other thing to note, clearly it can't be the case that Q can derive, it's not the case that for all x, 0 plus x equals x. To see that, so Q can't derive this, to see that, just take the standard interpretation. This is false on the natural numbers. The standard interpretation is a model of Q, so for the same reason, Q can't possibly derive the negation of that. So what we have is Q can't derive for all x, 0 plus x equals x. And Q also cannot derive the negation of this fact. 0 plus x equals x. And so because of that, we see that Q must be negation complete. Now, as I've already mentioned, I don't, strictly speaking, I haven't given you the full model because I need to know how do we interpret times in this model. So I need to extend this model to the full language. I'll leave that as an exercise for you. Okay, so I hope you get this is what I wanted to discuss in class today. And I hope you enjoy your snow day.